Thank you for the nice introduction. So everyone can hear me. So I will talk briefly about a starting project in collaboration between Uppsala University and RISE SICS, funded by the Foundation for Strategic Research. It is starting, so I'll discuss a bit initial ideas and starting directions. So the Internet of Things is one of the ongoing revolutions in ICT. I don't need to talk much about that, but to make it happen, we need to focus, of course, on many issues that are not completely solved, like reliability, low cost, long lifetime, and not least security. So security for IoT has become a concern, and it has been reminded to us by some attacks that have been widely publicized in the recent years. People have created botnets of IoT devices. People have been able to make IoT devices do stuff with the real world. And although some of these have been due to sloppy practices and easily avoidable, at least they remind us that things should be taken carefully also in the IoT case. So security for IoT, of course, is a cross-cutting concern where you need to do a lot of stuff, software, user management, system management, dealing with the physical vulnerability. So a project cannot solve all of these issues. So the focus of the project Assist is on the software aspect of security. And I'll talk a little bit about how it's done. So Assist is a project between Uppsala University and RISE SICS, funded by the Swedish Foundation for Strategic Research, who has timely started launching a focused effort on the security effort area. The challenge or the goal of it is to develop techniques that can be used by developers of IoT systems for making their software resilient against security attacks. And the participating groups here are at Uppsala University. Let's see if I find here. Is that okay? The verification group, where I'm in. The Programming Language Technology Group with Kostis Sagonas. RISE SICS in Kista, where we both have the Networked Embedded Systems Group, who are developing the Contiki-NG system. And the Security Lab, Shahid Raza, who is the organizer of this event. And we also plan to contact the reference group of SMEs who are doing IoT software development. So I feel it's a very exciting team together, and we combine different expertise to address this important concern. Okay, so looking now at the landscape of stuff that goes on in IoT, there are several platforms. Perhaps the leading one is, of course, we are in Kista now, so it must be Contiki. Contiki was started at SICS, RISE SICS, maybe I should say that now, it's politically correct. Okay, and it's a Swedish system, and it has evolved into a Swedish ecosystem with several companies. One of the things that makes it leading is that on a small platform, it has managed to put a communication stack that makes all the standard communication possible with the external world. It's fair to say that it's the unique, well, it's leading in this aspect. And in fact, this communication stack is made quite dependable and also available for a number of small platforms like Cortex M0, Cortex M, several of these. Okay. One of these platforms is typically a small device with not so much memory, a CPU, not so fast one, radio interfaces. It has a power source. Battery can also do maybe even harvesting, and can also be connected to a number of physical sensors and actuators. And the characteristics of these devices make some aspect of software security difficult. So the fact that these devices are in contact both with the internet, with a wireless interface, and you can even steal them physically makes it hard to secure them. Typically, the devices have small resources, meaning that you lack some of the support that you typically have in your normal Linux system. Like memory protection is not available on all these small platforms, so meaning that when you can get access to a part of the system, you can sort of, you don't have a kernel mode where you cannot intrude. You cannot put software to detect intrusions and mitigate them. And typically, you don't have a model for installing new components that replace faulty ones. And also this makes for programming in a very optimized style, not using defensive programming. So bugs easily get into there. And also there is a lot of platform-specific ways to program these ones. So with these concerns, we structured the program or the project into a number of directions. So the first one is just dealing with analyzing the software for vulnerabilities or bugs or things that can be exploited by attackers. Second is the network aspect, which deals with software, complementary to the previous talk. So the previous talk's about the protocol as is, whereas we talk about the implementation of the protocol. Does it conform actually to the assumptions made by the verifiers using Tamarin? And the third is to catch up a bit with the fact that we don't have the normal mechanisms that you have on larger systems, such as memory protection, monitoring. How can you do this on a small platform still? And we will try to develop general techniques, but of course, living here, we will have to look at specifically about Contiki and some of the important protocols in the Contiki world. For instance, DTLS, this one, and maybe some more that were discussed in the previous sessions, also before lunch, like OS Core, maybe. Okay. So let me talk first about. So I'll talk now about each of the three directions a little bit. So first one is software analysis or software verification. So here, very roughly, the world of software analysis can be divided into dynamic techniques where you test or you simulate and you try to see whether there are bugs and you find them. Or the other one is static techniques where you look at the code and see whether there is an app. So you try to see that, okay, check that there is no possibility for bugs. And the first one is the easy one where you just do testing and it scales well and whatever you find is a bug. Second one is more like you look at the language and there can be difficulties to deal with all the language constructs. And on the other hand, you can provide guarantees because if you don't see a possibility for errors, there is none. Whereas here, if you find bugs, you don't know if somebody remains. So in this project, which we go for the first half year, because actually this class of techniques has developed quite rapidly in the last decade or two, surprisingly well, I think. So we think it's a good way to see whether we can even improve on that and apply it to the IoT systems that we see. So let me just give some background because I think it's fun. So so to do this, the name of the game is you instrument your code so that you can easily find the errors you're looking for, maybe memory errors. Then the hard part is then to explore all the possible paths in your code and see whether any of them can lead to a violation of whatever property you want to verify. So the easiest way to do that is, of course, random testing. This looks stupid, but we have things like property-based testing, which is essentially this, and it works very well in some cases. In Uppsala, we have this brand called targeted property-based testing, which tries to make this monkey slightly more intelligent. Okay. Another way to make this monkey slightly more intelligent is to make the randomness a bit targeted so that instead of just producing random inputs, you have a number of good inputs that are likely to find errors or that are likely to exercise different paths in your code. And then you change them a little bit so that you find other paths, hopefully. And then you send these mutated inputs to the target system. Still, this is black box. Although for these techniques, of course, you can quickly exercise a very large number of tests, but it's hard to find paths that require specific conditions in your input, such as passwords or specific keywords in protocol messages. So the opposite of that, which really tries to see how can be clever in finding new paths in your code, are called Whitebox Fuzzing, or also called symbolic or concolic execution, where you first instrument your code. So it's not really black box, we call it white box, so that whenever you exercise a path, this instrumentation collects information about the conditions in the code that you have exercised, and then you can analyze this to see how would I do to find a new path in my code, and then you exercise that, and then you go on. And this approach has been quite successful. For instance, at Microsoft, there is a system called Sage, which has been able to find a lot of security bugs in software that they release on the Windows system. A problem with this, okay, it's quite good at finding new paths in the code, But compared to previous approaches, the overhead per test case is 2-3 orders of magnitude. So recently, a third compromise between these approaches have appeared called maybe Greybox Fuzzing, also with surprising efficiency, where instead of just collecting all the path info, you do lightweight instrumentation, collect only some information, typically what is the path in the system that you have exercised, and using this info to guide the mutator or produce seeds for the input mutator. So you typically produce seeds that are likely to find new paths in the code that were not exercised before. So compared to previous approaches, here you can have a rather quick, very many tests exercised per second, and surprisingly efficient in finding new paths, although not as good as the Whitebox approaches. But still, this American fuzzy lop has been quite widely publicized in recent years and been very successful in finding bugs in even well-tested software. So for the project, our goal is, of course, to improve on these techniques, use them even further. And some of the things we want to deal with here is to worry about stuff that you find in IoT software, such as how checking that you use device-specific paths of software in a good way. Another thing that has not at all been considered in Greybox Fuzzing or a lot in fuzzing is concurrency. And on some platforms, you have that in form of interrupts. Interrupts can lead to many new paths in your code. But if you want to analyze them efficiently, you have to be clever in limiting the ones you explore. And we have previously done a lot of work on multi-threaded software, for instance, in the Linux kernel. And we try to exploit that also in this context. Okay, so just as a side issue here, we have also in the Contiki team is also maintaining some bug lists. And here is just an excerpt of some stuff that was reported and fixed. So you can see here that typical issues reported for Contiki, like with many other systems, are the stack-based buffer overflow that is potentially a security vulnerability. So hopefully with the project, after a while, we can find all of these, and there will be no more reported from the wild. The next topic is communication security, so complementing the previous talk. So what about implementing protocols in the IoT world? So here is a protocol stack of low-power IP version 6. So you have a standard protocol stack, and to make it secure, you add on top of that secure versions. So for instance, for the TCP layer, you have TLS. In Contiki, you have UDP as a transport layer, and the corresponding secure protocol that is the DTLS. So just taking this as an example, so for TLS, I think there was some mention about TLS in the previous talk. So implementation correctness is important, of course. And in fact, there have been a number of issues reported in recent years, not relating to the protocol, but to its implementations. So, for instance, there have been a number of attacks exposing cryptographic implementation weaknesses, so that if you don't implement them properly, you can expose side channels. This is nothing that Tamarin would discover. Also, you can send the input messages not assumed to be received, and this may in some case bypass authentication. So all these things were discovered by people in the area. And one of the approaches, not the only one, but one of them we will approach, which is based on, so to do testing of this, you need some kind of a model of the protocol, what it should do. And typically, you don't have it on the internet. So let's try to see whether we can produce it. So one way to produce it from implementation. So there we will use a technology that we have partly developed in previous projects called model learning or automata learning or so on. So it's based really on, you have here some black box system that is doing something, and you want to make a model of its behavior. And if we take a simple approach where the interface is just a set of simple symbols, you can interact with it a bit, produce many test messages, you produce a model of its behavior, and after a while, you create a model which is the least way to explain the interaction you had with this target system. Okay, so this is well understood in the finite state case, but now we live in the real protocol world. So if now this black box system is a, say, TLS server, then you don't send just the client hello. So typically the first message you send when you want to talk with the TLS server is a client hello message. But this is actually a complex thing. So it has many parameters. So in order to deal with this, you need to understand how this thing relates to that. So what you do that is, of course, you put a test harness of some form. And now you can play your learning technology here. You have a test harness that takes care of all the parameters that need to be put into messages and understand the responses. And in fact, this has been done for TLS, and experiments have been done on various implementations of TLS, like these ones. And you can see that, okay, here you see the normal message, you send some handshake, and after a while you can send application data. But for some implementations, you receive some surprises that are discovered in this way, so that if you send messages that are out of order, so for instance, you don't send cipherspec specification, you just send, now we have a handshake, then some implementations assume that the cipherspec was already decided. In fact, it was not, and so you can send data in clear text between the server and the client. So, okay, so things of this like this can be discovered using this technology. So some of the ideas we have are working on is to do that for DTLS. So in fact, such a test harness is quite complex, because if you want to develop to find cryptographic attacks and things, you need to implement all these cryptographic primitives and also attacks that exploit them. So we are collaborating with a group in Bochum who has developed a powerful such tool for TLS, and it can be retargeted for DTLS. And the idea is, okay, so we make the corresponding thing for DTLS in progress. And using this model, we can then check many of the assumptions that used in Tamarin, whether they hold for this implementation. We can also check vulnerability. So these side channels will show up as state transitions in this model. And also, they will be useful seeds for fuzzing, whether you can find other vulnerabilities in the protocol implementation just by taking a long sequence of messages and mutating it slightly. Okay, finally, the topic about putting runtime support for various protection mechanisms. So just as I said, so some of these platforms don't support memory protection. One of the approaches we are working on is to use ARM Trust Zone, which is coming out. And this is a way on ARM platforms to provide one secure world where you can put data and code which is inaccessible from other applications. So you can put kernel operations, you can put cryptographic information here, you can put stuff that what peripherals you want not others to manipulate. So the challenges are a bit to understand how to properly implement such a thing on a platform like Contiki. How you provide communication of data between the secure world and the normal world. This is not a trivial thing. And furthermore, many of these small devices, they operate transiently. They compute for a millisecond and then they sleep for an hour. And when they sleep for an hour, you want to store all the data in the secure world, because when they sleep, people can steal it and get all your data, but you don't want that. So these issues are being explored. Another thing is about updates. So we are working on a protocol called SUIT, of course, to do updates of components in IoT systems. It's based on PKI, so it's implemented and evaluated for Contiki, and also a system for remote software upgrading entire firmwares over the internet. Of course, this also requires some infrastructure, and you have to make sure that this infrastructure is secure so you don't accept malicious firmwares on your platform. Okay, so to summarize, security is a critical concern for IoT software. So this project deals with the software aspects of that. We are working along 3 major directions. One is just normal software analysis, testing, verification. Another is to secure protocol implementations, to do the networking. And we are also trying to enhance the power the platforms themselves, so that they will be more agile towards mitigating software threats. And we hope that techniques will be usable by developers of IoT systems in general, and also, of course, for making Contiki a bigger success than today. Thank you.